So what I'd like to do to kind of wrap up the discussion about parallel streams is talk about when to use them and when not to use them. So we'll first talk about the circumstances under which it makes sense to use a parallel stream, which is almost always when your applications have this embarrassingly parallel property. And then we'll also talk about when not to use parallel streams, which occurs when they don't have the embarrassingly parallel property and/or there are other factors like there aren't very many elements to be processed or each element doesn't take very long to run. If those are the circumstances, you don't want to use them. The first thing to remember about a parallel program is a parallel program always does more work than a non-parallel program. How can that be, you might ask? Well, the first thing that has to happen is it has to partition the problem up into chunks. So that's extra work. Then it has to do the processing. Of course, you always have to do the processing. That's typically all a sequential program does. It just does processing. And then it also needs to combine all the results back together again. And it turns out that steps 1 and 3 are above and beyond what you would have needed to do for a sequential program, because a sequential program doesn't have to partition, and a sequential program doesn't have to combine. So there darn well better be something that you get as a win by doing all this extra work. And therefore, if that's not the case, if all this extra work is for naught, if you do all this extra work and it doesn't give you a speed up, then it was a waste of time trying to do things in parallel. But you're the one who has to figure out when it's good and bad to do parallel processing. Parallel streams follows your command, but doesn't really try to think for you. So it's just sort of blindly following what you're telling it. And you might take a look at this link at the bottom, Stream Parallel Guidance, which was written by the Java Streams experts and gives you some tips on when to use streams and when not to use them in parallel. And I'm going to summarize kind of what it said. So here's the circumstances under which you should use parallel streams. When your behaviors have certain characteristics. First of all, are they independent? Are they embarrassingly parallel? Do they have little or no dependencies or need to communicate between tasks or share results between them? The best of all possible worlds is when there's no dependencies and no need for sharing, because then things can all run at the same time, much like many loads of laundry in the laundromat, where they don't depend on each other. They just all run at the same time. You can get a lot of stuff done simultaneously in parallel. So searching for phrases in a list of input strings containing the works of Shakespeare. That's a great example of a highly parallel program that's embarrassingly parallel. And that's exactly what we did with all these different implementations in our Streams Gang solution. And you can see that so far for searching for phrases in input strings, which one is it? Search with parallel splitterator was the fastest way because it had the most amount of parallel processing compared to everything else. It searched for chunks of phrases in parallel, it searched chunks of input in parallel, and it searched chunks of each input string in parallel. So there's lots of different ways that things run in parallel. Another thing to consider is how computationally expensive are the processing tasks that you're actually running, or the behaviors. So if it turns out that you have behaviors that take a long time to run, like you're going to do some kind of convolutional neural network, or you're going to do some kind of very expensive task, like trying to figure out whether a big number is a prime number, which takes a long time to run. That kind of processing really benefits from being run in parallel. Likewise, if you have lots of elements to process, right? If you've got zillions of things you have to work on, once again, parallel processing would be a win, right? If you had the task of dusting off all the terracotta warriors, you would probably spend a lot of time by yourself doing that. That would take you a long time because there's lots of terracotta warriors here, right? Conversely, if you had, 5 groups of people doing this, it would go a lot faster because they could run in parallel. So if you have lots of things to work on, it's going to be a win. Especially when you can split up the work in an even way. So again, coming back to this example, right? Each of these lines of terracotta warriors is roughly about the same size, and so if you have a team of people working on it, you'll get a win. So splitting things evenly and splitting things efficiently is also a very important consideration here as well. So if these things apply, then you can build a model to give you guidance on whether or not parallel streams processing is for you. And this is something that's called the NQ model. And that term was coined by Brian Getz, who's an architect at Java, who was responsible for a lot of the parallel streams design. And here's the model. N is the number of elements to process, which could either be high or low. And Q is a weird acronym. I don't even know what it stands for. I say it stands for quantifying the time spent on each element. So each element of the N elements. So Q is a quantification of how CPU intensive the processing is. And so if you have high processing versus low processing, then Q is going to be higher. So if N times Q is a bigger number, you're more likely to get a benefit from parallel streams. If N times Q is low, either because you have a small number of elements or the processing on each element is very, very minor, it's probably not worth doing it in parallel. And the reason for that is because there's all this startup cost to partition and all this merging cost to join things back together again. So you've got to find some way to do better than just doing it the naive way of taking all the time to do those splits. A good example of something that worked fairly well was to use the phrase match split iterator, which split the input strings up into chunks that could be used to search for these phrases in parallel. And that was something that allowed us to, if we had lots of elements, we had more elements to search in parallel, and the searches themselves are not wildly computationally expensive, but searching for a phrase in a string does take some processing time. So it lends itself nicely to being parallelized. Sort of an obvious thing is, do you have multiple cores? If you only have one core, all of this stuff is probably overkill. All of this stuff is a waste of time. Now, keep in mind, thinking way back to the beginning of the class when we talked about why did they even bother with any of this stuff in Java, fork join pool, parallel streams, and so on. It's because increasingly we have lots of cores, and we have to find some way of keeping them active, making them do something useful. And other forms of programming didn't lend themselves to scaling up the benefits of multiple cores. So having multiple cores, of course, is important to make the decision. So if you've got the right conditions, you've got the right kind of problem where N times Q is high, you have lots of cores, then you can get a big speed up. And as we can see here, the sequential version is relatively slow compared to the different parallel streams versions. However, everything is not unicorns and rainbows. So there are certain types of streams that are not suited, there's certain types of programs that are not suited for parallel streams. So it doesn't make any sense to use the parallel stream model in that case. So what might that be? Well, one obvious one is if the source of input that you're trying to process in parallel doesn't lend itself to efficient splitting, or it lends itself to uneven splitting. If it doesn't split evenly and efficiently, then it's probably not going to get much of a win, if any win at all, from parallel processing. So let's take a look at an example. This is from my EX14 folder. And what you can see here is we had an array of all the words in Shakespeare. So we have all the words in Shakespeare. We opened up all the works of Shakespeare, and we split them up by basically words. So we have all the words of Shakespeare, and it's a big array of them. OK, so it's basically implemented. This particular array, all words, is implemented as an array list, which is almost identical to the array that you wrote for your assignment. We also, just for comparison's sake, then took our array of all the words, and we wrapped a linked list around it. So now we have a linked list of all the words in Shakespeare. So you have a list of all words and an array of all the words in Shakespeare. And now we're going to count the number of words in Shakespeare. Again, it's kind of a silly example, but it illustrates the point very nicely and concisely. So if we say array all words dot parallel stream, and then we count the number of words, or we say list of all words dot parallel stream count, it turns out that the array version runs way, way faster. Even though it's the same number of words, and even though they're both running in parallel. And why is that? The reason for that, of course, is because this splits really nicely. Remember, if you think about your split iterator from your array or the array list, it basically splits things up evenly just by adding low and high and dividing by 2. So it's really fast, it's really even. Conversely, the linked list approach does not split evenly, does not split efficiently, and so its performance is dreadful. So don't use linked list for parallel processing is the bottom line. And here's just this is just a reinforcement of that, right? So here's the try split method from the array list splitterator. That's part of the Java collection. So we basically say low plus high divided by 2. That's the midpoint. And then we split things up. And notice, by the way, for those of you who are doing your splitterator for the current assignment, you have to make sure that you update the right-hand side by changing its index to the midpoint. We're giving back a new array list splitterator here that will be from low to mid, but then we also have to have a side effect of updating this splitterator by setting index to be mid. So now it's going to cover the range mid to high. That's basically how that works. Question? Why can you not split a linked list? Well, here, let's take a look at the implementation of the linked list splitterator. So one of the problems, of course, is, well, first of all, why is it so easy to split the array list? What makes it absolutely trivial to do it in, like, constant time?
Index-based.
Right, it's random access. The key point is, index-based access. It's a contiguous chunk of memory. You have the beginning, you have the end, you find the middle. So you can find the middle with one operation, and splitting just becomes essentially resetting the two chunks to be, the first half followed by the second half. Super fast, super easy. What's wrong with a linked list? How long does it take to find the middle of a linked list? Linear time, right? O of n time. It's actually n divided by 2 time. And you have to follow all the pointers, right? So you can't jump to the middle in one operation. So it takes linear time to find the middle. Now, they don't even bother trying to do that with Java. The Java linked list splitterator doesn't just scoot down the list till it finds the middle and then, updates the list and has the first chunk of the list handled by the splitterator and the second chunk of the list handled. They don't even bother doing that. That would take, I don't know quite why they don't do that, but that's not what they do. Instead, they have this really crazy code that creates a separate array of size n, where we have this thing called batch plus batch unit, and that gets updated as we're running through this loop. And it goes through here, and it assigns the current elements in the linked list into this array, and then we go ahead and we'll create a chunk that has like the first batch plus batch unit elements in the list. It's very complicated, very slow, and doesn't split things evenly. So as a result, it's much slower. And that's why you can't split a list in half in constant time. Any questions about that? Yeah.
So would using...
Possibly, yeah. It all depends on the value of Q. So we'll see that in a second. Might not be, if the processing of each element is very high, then a parallel stream might still be a win, but you'd have to be, you'd have to really sit down and benchmark it, honestly. It's very hard to know in the abstract. Yeah. Splitting it, well, this thing doesn't go halfway down. What's that? So what does it mean to do split unevenly? So this code here, well, first of all, why do we want to split things evenly? What on earth is the win of splitting things evenly with the parallel streams approach? Why is that a good thing? Why is splitting evenly good? Right, so, and think about your binary tree experiences in data structures class, right? If you have a perfectly balanced binary tree, what's the depth of the binary tree? Log of n. If you have a binary tree that's not balanced, how much do you have to traverse? Let's say it's the worst case binary tree. It's n, right? So if you split things up in a way that is not even, you're going to have lots more stuff to be done, and it won't be balanced. And so you'll have one core having to do all this work. The other cores will be sitting around twiddling their thumbs, maybe getting lucky and stealing, the occasional small chunk that shows up from the other core, but you won't get this wonderful balanced binary tree effect. So that's why splitting evenly is important, because it is able to use the logarithm properties of balanced processing. So you have better work, and the cores can work in parallel more effectively. That really has to do more with the way that fork join pool is implemented, but it's implemented very cleverly to work off of balanced processing. The other issue here is the startup cost of parallelism can overwhelm the amount of data. So let's take a look at the issue here. So here we have a parallel stream factorial implementation, and here we have a sequential stream factorial implementation. You'll notice that they're identical, except that this one has the word parallel and this one does not. So the top one has the word parallel, the bottom one does not. If you give a value of n that is small, like 20, then, in fact, up to a fairly large value of n, the sequential stream will actually run faster. And that's because it doesn't have to do any splitting, it doesn't have to do any joining, it just goes ahead and goes down there and does the multiplication really fast. So it's not until you get a value of n that's really big that you're actually going to get a benefit here, because the startup and merging costs of parallelism is just higher. Remember we talked before about how there's always more work to be done in a parallel program than a sequential program? Well, that's exactly what the issue is here. A related problem, and they often kind of go together, but they're not identical, is the cost of combining the results is expensive. So it's expensive to take the partial results and merge them together again. Some parts of the world are very complicated to merge things. If you ever traveled to certain countries, actually, sadly, Nashville is becoming like this too during rush hour, but it's just chaos and insanity trying to get everybody to merge together. So this example illustrates this point. This example has a linked list of all the words in Shakespeare. And so that's kind of what we start out with here. We have all words is a linked list of all the words in Shakespeare. And then we go ahead and we take all words and we are going to go ahead and collect this thing into a set. So remember, sets are these balanced trees, is a tree set in this case. And a tree set is a balanced data structure that has no duplicate items. And the reason why this performance is so low is that it has to break up those words into partial subsets, and then all those subsets get merged back together again to get a final result. And merging two sets together is fairly expensive, because you can't just append the results of one set to the end of the other one, because they won't be in order and they won't be deduplicated, right? So they have to be merged together, sort of, one element at a time, merging it into the set. So that turns out to be very slow. So merging sets together, that by the way, also is why we have concurrent collectors, because merging partial results for some types of data structures is expensive. The only possible way this is going to be a win, and this comes back to your question from a minute ago, is if what we do between parallel stream and collect is expensive. Now, if all we're doing is just merging, then oh well, too bad. But if there's a lot of processing that was to be taking place here, then the queue could start to offset the fact that the merging costs were high. And the same thing is true for the splitting costs. If splitting costs are high and merging costs are high, but queue is so huge, you might still get a win. But I wouldn't count on it. So you have to benchmark and see for yourself. This is a good example of when it may pay off to use a concurrent collector. So rather than using a sequential collector where we're using two collection with tree set, this is a sequential collector that merges the partial results. We could use a concurrent collector, in which case there is no merging of partial results, because all the processing takes place by putting the results into a single mutable collector that's shared by all the threads. Now, obviously, that single mutable collector had better be thread safe, and it really helps if it's also efficiently thread safe, as concurrent hash set collector is that we've talked about before. But that's one way you could offset the costs of dealing with collectors that are expensive to merge. Yet another problem. Certain Java 8 features don't enable sufficient exploitable parallelism. And this is a really surprising thing to stumble across. I found this when I was working on some version of my examples a year or so ago, and somebody wrote to me and said, I've been playing around with streams, and I notice when I do this kind of programming, and I run it in parallel, it's really slow, and it has all this extra work that's going on. What the heck is going on here? So I wrote a little example, taking his program and then rewriting it to be a lot more efficient. So this program, what this program is trying to do, let's say that we have, let's say number is 100. So this is going to try to find the first 100 even numbers and get the square root of them and put them into a list. So we'll end up with a list of the square roots of the first 100 even numbers. That's what this is trying to do, or that's actually what this does. So it does this by making an iterator where it says start at 2 and every time add 1 to the previous value. So it'll just go through there and generate all the numbers from 2 to number, 2 to n. In parallel, it'll filter out only the even numbers, so it only keeps even numbers. We only go up to 100. And for the ones that are even up to that amount, we find their square root, and then we collect the results into a list. This runs really, really slowly, and that's because iterate and limit split and parallelize very poorly. Conversely, here's another way to do the same thing that's way faster, and it parallelizes very nicely. This uses another method called range. So range starts at 2, and it's going to go until number times 2 plus 1. So that's the number of numbers. That's the number of numbers that'll be generated by range. It runs this in parallel. It filters out the even numbers. It computes their square root, and it collects the results into a list. This will run really fast because range parallelizes and splits evenly. So it's much more efficient than that. But they compute the same result, but this approach uses features in Java that don't parallelize very well. So it's important to remember that. It's kind of a rare thing, but it's important to realize. Yes, Allison? Yeah, that's correct. Oh, but it's range, not range closed. So range will go up to that, but not including the final number. If it was range closed, it would go to 201. I could have also, to answer your question, I could have also said range closed to number times 2, or range to number times 2 plus 1. Because range closed just says include the very last number, but we need to be able to, we're trying to get the first n even numbers, so of course we have to go twice as many because half of them are going to be odd. So, whereas this one didn't have this issue. This just kept generating numbers until we had found the first number of them that were even. If that makes sense. So it's fun to run this example. You can see this at the code down there, and it's just way faster. And obviously, if you don't have any cores or don't have many cores, what's the point of that, right? So if you have these older computers that only have one processor, parallel streams are most likely complete and utter overkill, and you wouldn't even think to do stuff like that. Another interesting thing to remember is that there's no easy way to shut down the processing of a parallel stream, which is really wacky. I'm not quite sure why they didn't make that as one of the features in a stream. So once a stream starts to run, it's almost impossible to externally shut it down. You can have code that within the behaviors that are called in a stream will do things that will be flags to indicate that they should shut down or throw an exception or whatnot, but you can't just say stop the stream. And that's in contrast to some other concurrency frameworks such as the executor service, where you can actually shut down an executor service and all the threads that are running inside it. But once a stream starts to run, it's very hard to shut down. That's indicated by the sorcerer's apprentice metaphor here, where, as we learned from the Sorcerer's Apprentice, from the Fantasia movie of Disney, once you set things into motion, it's often very hard to stop them from going in motion. Okay, so hopefully at this point you have a little better understanding of when to use parallel streams and when not to use parallel streams.